Hi, my name is Leonard Schneider, and I'm going to summarize our paper Tackling Neural Architecture Search with Quality Diversity Optimization. And this is joint work with Florian Pfisterer, Paul Kent, Jürgen Branke, Bernd Bischel, and Yannick Thomas. So consider the scenario of optimizing two objectives, the validation error and resource usage. And in multi-objective NAS, you typically want to find or approximate the true Pareto front. So there's like this concept that if objectives are competing, there is no single best solution, but there are multiple solutions, so a set of solutions, so the Pareto set, and in the Y space, the Pareto front, consisting of architectures that trade off performance with respect to the objectives. So for example, if I use fewer resources, typically my validation error will be higher. If I use more resources, typically my validation error will be lower. And a good multi-objective optimizer then is capable of approximating this true Pareto front quite well. And this Pareto front is shown in black, but take a step back and consider why are we actually doing multi-objective NAS? Typically, we do this because we want to deploy different models in practice. So we have different target devices with, for example, different constraints on resource usage, like model size or latency. And multi-objective NAS is then capable to find a diverse set of solutions that probably fit on these devices. But we argue that, in essence, once we've met an architecture that fits on a device, we do no longer care about minimizing resource usage any further, but we rather then only opt for optimizing performance. And this is visualized in green. So the vertical lines are so-called niches then, and here they directly reflect constraints on hardware devices. So once I am within a hardware constraint, then my goal is to find the best architecture that fits on this device. So the green points are actually of interest and not the whole Pareto front. And this is essentially solved by formulating the multi-objective NAS as a quality diversity optimization problem. And this is what our paper is all about. In multi-objective NAS, I minimize two or more conflicting objectives simultaneously, for example, validation error and model size, and I try to approximate the true Pareto front. So in contrast, but also related, in constrained NAS or hardware-aware NAS, I solve a constraint optimization problem with a primary objective, so optimal performance is my goal, but I have a secondary constraint on, for example, model size, latency, or RAM, for example, and then I solve a constraint optimization problem. So what you do in quality diversity optimization is to find high-performing but diverse solutions. So again, you want to find multiple solutions, so you return a set of solutions, like in multi-objective optimization, but you do not aim for approximating the true Pareto front, but you want to find for each so-called niche, which we will later see, that are defined on so-called feature functions, the best architecture with respect to performance. Quality diversity optimization has its origins in the robotics NDA community. So just to drop some names, novelty search and map elites being the first QDO algorithms. And again, while constraint optimization seeks a single optimal configuration given some constraints, QDO aims to identify the optimal configuration for each of a set of constrained regions in feature space simultaneously. So in essence, we solve a set of constraint optimization problems jointly or simultaneously. And in NAS then, the primary objective is given by performance, for example, validation error, and feature functions are then given by model size, latency, or flops. So to get a little bit more formal, assume we have an objective function f1 mapping an architecture to, for example, the validation error. Then we have multiple feature functions, k equal or larger than 2. And these also map architectures, but to, for example, memory usage or latency or model size. These are the feature functions. And then behavioral niches are sets of architectures that are characterized via boundaries on the images of these feature functions. So for example, a boundary could be on latency where I say, well, the lower boundary is 10 milliseconds, the upper boundary is 30 milliseconds, then this is a niche defined on this feature function latency. And an architecture then simply belongs to a niche if its values with respect to the feature functions lie between the respective boundaries. And the goal of a QDO algorithm is then simply to find for each niche the architecture that minimizes the objective function. And again, this results in having multiple solutions. So for each niche a solution, and you return a set of solutions. We introduce in our paper 3 quality diversity NAS optimizers that are mostly model-based. So we introduce Bob Elites, that is using Bayesian optimization for quality diversity optimization, but adapted for neural architecture search. So this is based on Bob Elites, a quality diversity optimization algorithm, but we use insights from bananas to make this usable. So we have a new acquisition function, the expected joint improvement of elites. And this is simply the weighted sum of the improvements per niche. So I have C niches, then I sum the improvements for each niche. So this is on the right-hand side of the equation. And I weight this improvement by the posterior probability of an architecture belonging to a niche. We also adapt hyperband to the quality diversity setting because in NAS, it's quite desirable to have multi-fidelity evaluation, and hyperband is known to be well-performing. This is done by proposing architectures for promotion uniformly over the niche. Finally, we combine quality diversity hyperband with Bob Elites, resulting in an algorithm we dub Bob Elites hyperband, in essence, Bayesian optimization hyperband, but for QDO. So here are results on our main benchmarks experiments on NAS Bench 101 and NAS Bench 201. So I'll guide you through the figure. So for each of the benchmarks, so for example, NAS Bench 101 on Cypher 10, we constructed different problems by considering different number of niches. And we dubbed these then small, medium, and large settings for the number of niches. So in the small number of niche setting, we only consider 2 niches of interest with respect to model size measured by the number of model parameters. And then we have, for example, the small niche up to the 50% quantile of architectures with respect to model size, and the other niche would be 50% to 100% quantile of the architectures with respect to model size. And then again, in the medium and large setting, we consider 5 or 10 niches of interest. So increasing number of niches essentially. On the x-axis, you see the total budget used. So simply the total number of epochs used. And on the y-axis, you see the average validation error for each niche. And this is summed up over the niche, because like the goal in quality diversity optimization is to find high-performing architectures for each niche. We observed that, first of all, quality diversity optimization in general outperforms or performs on par with multi-objective optimization. We also observed that the model-based hyperband variants strongly outperform the hyperband variants. But eventually, the purely model-based optimizers like Bob Elites or ParEgo catch up with the model-based hyperband variants, which is the expected behavior. But again, you can get quite some performance boost by combining hyperband with model-based guidance. I also want to give a glimpse at additional results in the paper. We have another benchmark where we compare quality diversity NAS optimizers to multi-objective NAS optimizers on the MobileNet version 3 search space, where models are deployed on a Samsung Note 10. And we observe similar good performance of quality diversity optimizers, in general, always outperforming the multi-objective ones. It also shows how QD-NAS can be effectively be used for model compression, where we show that you can tune the hyperparameters of a neural network pruner to achieve high-performing architectures in different niches with respect to model size. And we also show that the concept of QDO is orthogonal to the actual NAS method that is used. So we illustrate that, for example, in Once for All, you have a pre-trained supernet, and this supernet is then searched via regularized evolution for subnets that meet certain target device constraints. And this regularized evolution part can effectively be swapped out with a QDO optimizer. So for example, using Map Elites. And this makes this joint search, if I am interested in finding multiple architectures for different constraints, then this joint search is made more efficient by using QDO instead of having this repeated regularized evolution. So thanks for your interest. Make sure to check out our poster, and I'm happy to discuss any further questions or get in touch with you at the conference.